Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures in thermodynamics. Today, we are looking at the efficiency of the Otto cycle. We have talked about the Otto cycle in our earlier lectures. Let's just look at the efficiency. Let's just remind ourselves of the Otto cycle. It comprises of 4 processes. Let's remind ourselves: pressure, volume diagram, cylinder, pressure, cylinder, volume. Let's just remind ourselves. One, step 1, 2, 3, 4. And on the temperature entropy scale axis, entropy, of course, is temperature. One, two, three, 4. So we just remind ourselves quickly that for 0 to 1, we have intake of air into the piston. In other words, the piston is moving down towards the BDC. That's the bottom dead center. This corresponds to the top dead center. At that particular point, then we have, of course, the air-fuel mixture. It is compressed. It is compressed. This is isentropic or adiabatic compression. As you can see, it's isentropic. If you look at step 1 to 2, it's isentropic. The entropy is not changing. The entropy is not changing, it's constant. And then here, we now have the ignition. We'll have ignition at this particular point. Notice at this particular point, we have the inputted heat. Heat inputted into that particular system. And of course, you can see, and at that point 2 to 3, the temperature is going up. And then now we have the master process. That's the power stroke. 3 to 4. 3 to 4, that's isentropic expansion. Isentropic expansion, you can call it also adiabatic expansion. And remember, it is reversible. It is reversible. And finally, we have the discard of heat. Heat is rejected, Q out. And of course, this will be rejected, can go to the engine cooling system, like where we have a system of radiator with coolant. And also some can be released through the exhaust pipe, that is as an exhaust fume. Now, we notice that again along those lines, here the temperatures are decreasing. The temperatures are decreasing. And that's an important thing for us to remember as we work with this particular system, so that you're not lost. But I encourage you to look at our discussion on the Otto cycle. Now, what is efficiency? Efficiency, which we call neta, efficiency, remember, is the network over the inputted heat. And what is the network? Remember here, we have isentropic compression. In steps, pay attention, in step 2 to 3, pay attention, in step 2 to 3, if you look at that step, 2 to 3 is isochoric. 2 to 3 is isochoric. Delta V is equals to 0. And if it is isochoric, there's no work. No work done. Because delta V is 0. Delta V is 0. There's no work done. And in the same note, we have step 4 to 1. Again, 4 to 1, that's isochoric. Delta V is equals to 0. Again, that's an isochoric step. So we have work done during isentropic compression and isentropic expansion. So we can talk of expansion work, neta, is W total, this W total will be W expansion plus W compression. And of course, so that has negative connotation at the interface, and it chews a large chunk of the work output. Now, so if we put these particular quantities, so we have neta, we therefore the work W compression over QH. But remember that from first law of thermodynamics, du is equals to dq plus dw. du is equals to dq plus dw. This is first law of thermodynamics for closed systems. First law of thermodynamics. So, because we're talking of a reversible cycle, du is equals to 0. Therefore, dq is equals to dw. What does that mean? That means that the difference in the work outputted and the work consumed, for example, by the compression, that difference is the same as the difference between the heat inputted and the heat rejected. The heat rejected. So that the neta there, you can still express the efficiency, neta, express the efficiency neta as QH minus QC over QH, which is 1 minus QC over QH. Heat inputted and heat rejected. Heat inputted and heat rejected. Remember, when we are dealing with Carnot cycle, just remember for your note, we are dealing with Carnot cycle, we add efficiency is 1 minus TC over TH in terms of those particular temperatures. So this becomes a very important quantity for us in terms of that. But remember that if we know what du is from first law, again, of thermodynamics, we know that du is equals to dq plus dw. du is equals to dq plus dw. And we know that when we are dealing with isochoric processes, there is no work which is done. So we can express du in terms of temperature change. We can express these particular quantities because what is du? Remember, du is Cv dt. And this quantity, we got it when we remember that u is a state function. So if you express a function of volume and temperature, then du was equals to del u del v dv, t constant plus del u del t dt, v constant, and this quantity is 0 to assume that the fluid or the gas is behaving ideally, and here this is Cv. So we have du is equals to Cv dt. Cv dt. And of course we are assuming that the heat capacity is constant. The heat capacity is constant. If you look at our earlier lectures where we talked about Kirchhoff's equation, you can express the heat capacity in terms, if it's dependent on temperature, if you're working in a temperature range where it depends on temperature, then you have to use that expression for heat capacity which shows dependence on temperature. Therefore, du in general, so if you take du for step, we have our system, remember? So we have our system, we have 0 to 1, 2, 3, 4. Let's just do it quickly. That is pressure, volume. So we are saying our du for step 0 to 1, this 1 to 2, that will be given by the mass flow rate times Cv into the temperature change T2 minus T1, and for the step 3 to 4, it will be given by the mass flow rate CV into T4 minus T3, where MF, remember, is the mass flow rate. CV, and we write again, is the isochoric heat capacity. And of course, T's are the temperatures. So in general, we have seen how we can express these particular quantities, especially for the efficiency of the Carnot cycle, of the Otto cycle. You have seen what you have there. That's the key expression for efficiency in the Otto cycle. So I think we'll stop at that particular point. We'll continue next time.